the lunch break. This room will be occupied by a seminar, so please take everything with you. And it means we also have to be on time, so it's for the speaker. The first speaker is Andreas Wallraff from ETH.
Okay, so yeah, thank you. Thanks to Dan and the other organizers for inviting me. So I decided to pick a project to talk about, which is strong coupling cavity QED with gate-defined semiconductor double quantum dots. I fear it's probably not going to be very many buddy-like, yeah, but I'm still excited about this subject. Playing ice hockey with Misha Lukin on this Saturday or so, we wondered when we first met, and it was probably here in this room that we first met about I think 13 years ago or so, when we managed to reach a strong coupling limit with superconducting qubits. And now you may wonder, okay, why do I bother to do experiments with semiconductor quantum dots? And the coherences are not quite as good as for superconducting circuits, but they're quite interesting systems. And I do think with using all these nice cavity QED techniques that we have developed for superconducting circuits in the past, more than 10 years or so, you can still learn new stuff about semiconductor nanostructures. Yeah? And so therefore, I think we set out to sort of deploy some of these measurement techniques in this other context. And so one of the main graduate students, or the main recent graduate student on this project, was Anna Stocklauser. She graduated last week, and currently we have two very good postdocs from Delft, Pascale Scarlino and David von Workom, working on this project. And we do that project in collaboration with the group of Klaus Enslin and Thomas Ihn, and materials come from Werner Wegscheider. Okay, so this is our current team here working in our lab, and I've been at ETH now since 12 years. It's pretty amazing. Time flies, and I'm indebted to collaborations with many colleagues at ETH and also with many students and postdocs in our lab. Okay, so why is cavity QED with superconducting circuits interesting? It maps this atomic physics systems very nicely onto electronic circuits, which are very simple to visualize in this sort of electrical engineering-like diagrams, yeah, where what is the dipole coupling between an individual microscopic two-level system and an electromagnetic mode can really be represented as a capacitor in the circuit diagram, where you have a single mode harmonic oscillator represented here by this parallel combination of an inductor and a capacitor, coupled to a superconducting qubit, where essentially the linear inductor is replaced by one of these superconducting tunnel junctions that behave as ideal, lossless, nonlinear inductors. And why is this nice? So it's nice because strong coupling is more or less easy, or is easy to realize in these circuits. Yeah, now actually we probably have to work hard for not being in the strong coupling limit when you make some circuit in your lab and you're trying to cool it down. It's relatively simple to fabricate and integrate, and therefore it's a good candidate for building quantum information processors and also building more complicated systems, for example, of the sort that Andrew Haug presented very nicely yesterday. And so out of this possibility to realize strong coupling physics, really a range of research directions have developed, and I'll just briefly mention them to just very briefly touch upon sort of other work that we do in our lab currently. So I would say there's three main directions using circuit QED, cavity QED with superconducting circuits. It's for doing basic quantum optics experiments, for working on quantum information processing and quantum simulation, and in this context of hybrid quantum systems, combining superconducting circuits with other physical systems. Okay, so I do have a few slides, and then so either you can look at the YouTube movie afterwards, or you could also ask me, and I can send you PDFs of the slides, which I'm happy to share with you. So this is a slide on just some not particularly recent selection of things that, as we've just discussed with Simon, with John Simon in the break, that have been published mostly in glossy journals on interactions of microwave frequency photons with superconducting qubits. And there's very basic things like vacuum Rabi splitting measurements to sort of sophisticated things like creating superposition states of photons in a cavity or making complicated cat states and the like, but also looking at parametric amplification processes and squeezing. And one thing that we liked in our lab was to look at this waveguide physics with superconducting qubits, where you can more or less get rid of the cavity and still have strong coupling between qubits and propagating photons. So one aspect that also motivated us to do this semiconductor work was the fact that our own lab has spent really quite a while on trying to not only analyze the quantum properties of radiation fields contained in superconducting cavities, but also try to develop techniques that would allow you to look at quantum properties of propagating microwave fields. And the aspect that makes that interesting is that once you can really look at quantum properties of propagating microwave fields, you could use the techniques that you've developed on non-superconducting emitters. Yeah, you could, for example, look at radiation emitted from a biased semiconductor quantum dot and ask whether the radiation has single photon nature or whether it's a thermal field or coherent or something else. And here's some examples of that sort. So this is a reconstruction of the Wigner function of a propagating microwave mode. You can look at emitter-photon entanglement and characterize that. You can do sort of Hongo-Mandel style experiments and measure second-order correlation functions or fully reconstruct multimode electromagnetic fields. So that's the density matrix of a Hongo-Mandel experiment on a beam splitter with 2 microwave frequency single photon sources. And you could look at squeezing of microwave frequency radiation. And we've developed a wide range of techniques to characterize these radiation fields. Then obviously you can use strong coupling in the context of quantum computation, and you've all heard a lot about it. And I think one of the current major goals is to implement error correcting circuits in surface code or maybe in other coding techniques. And that's something that IBM and Google and others are quite busy doing. And so while we're ahead for building systems with several tens or maybe hundreds or eventually millions of qubits, we're trying to look at doing quantum simulations with superconducting circuits. And there's these sort of variational quantum approaches for doing quantum chemistry. And yesterday, one of our works there was also mentioned using these matrix product states in Cavity QED systems to, for example, simulate the Lieb-Lininger model, which was something that Christopher Eichler did in our lab. And so maybe one other thing, and then there's all this nice work by that was sort of discussed early on in this paper by Andrew Haug and Jens Koch and others that looks at sort of photonic lattices built out of superconducting circuits. And sort of another topic that I sort of briefly was tempted to talk about here today, but then chose not to, is an experiment that we did in our lab, which is relatively simple, but which I do like a lot. It's a system out of 3 superconducting qubits. They're coupled both to a waveguide and a single microwave frequency resonator. And all these circuits elements can be strongly and controllably coupled to environments. And you can investigate the properties of bright and dark states and energy transfer between the set of qubits and then ask yourself questions about the dynamics of these systems in the context of light harvesting and photosynthesis. Which is something that I thought was very, very interesting, but which we faced sort of a lot of resistance from biophysicists who've been thinking about these problems for years and years, and they've been wondering a little bit about, okay, what do these superconducting circuit guys do in our field? And then we also had to notice that this experiments that were done at Berkeley like more than 10 years ago or so are still kind of discussed very strongly with strong opinions. But I do still think that our experiments there can sort of contribute something from a new angle. So I hope we'll get this published eventually, even though it turns out to be difficult. Okay, so if you have questions about that, I'm happy to talk to you afterwards. So we also do some quantum computing work in our lab together with Leo Di Carlo. So maybe the most complicated thing we currently are doing is we have sort of an 8-qubit device that you see here. So there's 8 qubits labeled here. They're mutually coupled by these coupling resonators, and every one of these qubits has a little readout resonator coupled to it with a little dedicated Purcell filter, and there's sort of a joint readout line that allows you to read out the quantum state of all these 8 qubits more or less in a single shot with parametric amplifiers and so on. And this is sort of an element that you could use in a surface code or in which you can simulate sort of linear chains of qubits interacting with each other. So that's a thing that we're currently also working on. But the topic of my talk today will be hybrid systems based on superconducting circuits. And so essentially any quantum system that has microwave frequency transitions, you could benefit from coupling it to a superconducting microwave frequency resonator. And there's many different examples, for example, mechanical degrees of freedom or ensembles of NV centers, for example, or you could couple Rydberg atoms to kind of planar superconducting resonators. Or the thing that we've started actually also now more than 5 years ago already is to kind of use gate-defined semiconductor quantum dots and couple them to superconducting microwave frequency resonators. And also there we would obviously follow the goal of reaching the strong coupling limit eventually, and that's what I'll be talking about today. So depending on how time will go, I'll have sort of 3 parts to this talk. So first I'll tell you how we've reached a strong coupling limit using these semiconductor double quantum dots. Then I'll discuss a little bit how we do time-resolved measurements of charge dynamics in these double quantum dots using circuit QED techniques. And towards the end, I might have, if I have time, I might briefly touch upon an experiment where we've kind of integrated a gallium arsenide-based double quantum dot together with a superconducting transmon qubit. And the idea is to provide a coherent interface between semiconducting and superconducting qubits. Yeah? And there's been nice progress recently in semiconductor structures for quantum information processing. And for example, out of Jason Petter's lab and also Lieven van der Zijpen's group, you will probably see lots of results coming out in the coming months or years. So these are the 3 topics that I'll touch upon. Okay. So what were we trying to do? We were trying to set up this hybrid cavity QED system. We combine a cavity with a double quantum dot. And you know everything about cavities. I think nobody has talked about double quantum dots yet. So in these gate-defined double quantum dots, you essentially use top gates on a 2-dimensional electron gas to define 2 puddles of electrons. You can control the separation between the 2 puddles of electrons. So if they get close enough to each other, electrons can tunnel back and forth coherently between these 2 puddles. You can inject electrons through a lead and extract them through a drain. And then you can wonder about how you could couple this type of system to a microwave frequency cavity and whether you can get coherent dipole coupling between the double quantum dot and the photons in the cavity realized in this system. And yeah, you all know how the strong coupling regime is defined here. And there were early experiments starting maybe in 2010, 2011, where people were trying to make different types of double quantum dots in different material systems, like gallium arsenide, gate-defined dots, indium arsenide nanowires, also using carbon nanotubes and even in graphene. And so the experiments that were done in these days, they all managed to achieve some dipole coupling between the electrons that tunnel couple between these 2 dots here. But none of the experiments actually reached a strong coupling limit. And the reason for it was that the decoherence rates of charges in these double dots were quite large. Yeah? The decoherence rate were typically on the order of a few hundred megahertz or even gigahertz. And that was a bit surprising also to see, because the material systems were really very, very different. Yeah? Sort of the decoherence rates were almost uniquely in this range, independent of whether it was indium arsenide nanowires or graphene or whatever else. While the coupling strengths themselves were quite sizable. Yeah, so the coherent coupling rates G were on the order of a few tens of megahertz or maybe even 100 megahertz or so, which are typical rates at which in superconducting circuits you easily achieve the strong coupling limit, because in superconducting circuits the decoherence rates were a lot smaller. So we then set out on worrying about sort of both how to increase the coupling strength and also how to maybe improve charge coherence in these devices. And it's also interesting to know that using these circuit QEDs, we were still able to improve charge coherence in these devices although you would think that, okay, there have been 15 years or maybe even 20 years of transport measurements in these devices, so what would you expect could you still do differently? Yeah? But I think we've now reached coherence times in these devices which on paper you would have thought should be impossible to realize, or nobody has really managed to reach those in regular transport measurements. Okay, so just very briefly for all of those who don't know how these quantum dots get made. So we start out with a gallium arsenide, aluminum gallium arsenide heterostructure that Werner Wegscheider grows for us in one of his MBE machines. So you start out with a gallium arsenide substrate, you put the aluminum gallium arsenide on top of that, you introduce a doping layer that creates charges, and then that creates this two-dimensional electron gas at the interface, and there's sort of a capping layer on top of your substrate. And then you're trying to structure the electrons in this two-dimensional electron gas by applying voltages to top gates. So the first thing that also already took a little bit of effort, sort of usually in semiconductor physics, these heterostructures are considered very valuable. So like somebody made them in a super expensive machine, and once you have a good piece of wafer, you're kind of trying to cleave it up in as small as possible pieces and do lots of experiments. And so it took a moment for us to convince people that, okay, the first thing that we're going to do is get rid of the two-dimensional electron gas at most of the wafer and only leave it in a small region to define a mesa. So we remove the two-dimensional electron gas almost everywhere. Then we put these ohmic contacts into the electron gas that allow us to inject electrons from the top of the chip into this two-dimensional electron gas layer. Then we pattern leads, metallic leads on top of that structure that we can then bias with voltages. And if you choose the right geometry and apply the right voltages, you could make two puddles of electrons in these regions, for example. And so we form our double quantum dot here, and then we couple that to a superconducting resonator. And here you already see a version, sort of a more sophisticated version that we've developed for reaching the strong coupling limit. So we've done experiments some time ago where this resonator was just a regular coplanar waveguide resonator with 50 ohm impedance. And while we were approaching the strong coupling limit, we actually thought, okay, how could we get another factor of 5 or so in our coupling strength? And we did that by going away from 50 ohm impedance resonators to resonators with much higher impedance. And one of the ways how to do that is instead of using a coplanar waveguide resonator, you use a squid array resonator where you can use squids to make very large inductances. And that's what I'll be discussing a little bit. So here you have a little squid array, and at the end of the squid array, you couple to one of the dots in your double quantum dot, which is formed here. Okay. So, okay, why would using a squid array be a good idea for doing a high impedance resonator? So the dipole coupling in these structures or in any structure is given by the dipole moment of your microscopic degree of freedom and the size of the vacuum fluctuations on your resonator. And so you can actually realize that the size of the vacuum fluctuations on your resonator is dependent on the square root of the impedance of the resonator that you're using. So you can increase the size of the electric vacuum fluctuations by increasing the impedance of the resonator. And that you know that the impedance is given by the square root of the characteristic inductance of the resonator divided by the characteristic capacitance. And so if you make a resonator with a very, very large inductance and a small capacitance, you can enhance the size of the vacuum fluctuations of the electric field component. And you could do the reverse if you don't want to electrically couple, but magnetically couple. So if you wanted to couple to a single spin strongly, you would also not use a 50 ohm resonator, but you would use one where the inductance is small and the capacitance is very large. And that has also been looked at. So then the question is, how can you make a large inductance? Yeah? And so making large inductances, you could just make a thin wire and make it long, and you get about a nanohenry per millimeter of wire usually. And so you really need a long wire to make sizable inductances. So, but then there is a trick that you can use you can use the inductance of a Josephson tunnel junction. And it turns out that the inductance of a Josephson tunnel junction is inversely proportional to the maximum supercurrent flowing through such a tunnel junction. And so here you could now look at this equation for the inductance of a Josephson tunnel junction, and you would say, okay, I make this critical current as small as possible, and then I will get a large inductance, which is true. But the problem that you would then have, you would make a nonlinear inductor also if this critical current was small. And so instead of using a single junction with a small critical current, you just use an array of junctions with a sort of a reasonably large critical current so that the total inductance is large enough to give you an interesting impedance of this circuit without your resonator getting too nonlinear. And then what you also want is you want to give it a small stray capacitance, because if it has large capacitance, it will also bring down your impedance. So here you see such a squid array. So here's a sort of a zoom in. You have a loop of a squid. There's two tunnel junctions here on the left and on the right. And you see these tunnel junctions are maybe a few microns long and a fraction of a micron wide. So they're much larger than the typical tunnel junctions that you use in superconducting qubits. And then you connect up these squids in a longish array, and typically we do maybe a few tens of these squids in series. And you then essentially use this squid array and its stray capacitance as the resonator, and by controlling the stray capacitance and the total inductance of the squid array, you set the resonance frequency of this resonator. Okay, so here's a picture of one of these. So that's one of the devices that we've made. So from the bottom here, you see these are these annealed contacts to the two-dimensional electron gas. The golden-looking ones are the top gates that form the double quantum dot. And in this region here, you see the squid array, and there's a drive line that comes in from the top. And if you zoom in a bit more, you see here the squid array. It's separated by the ground plane by a fair bit to reduce the capacitance of the squid array. And then it has this sort of terminal here that extends down towards the bottom, towards this semiconductor double quantum dot. And in this case, the squid array has 32 squids in it that you see here. And so this finger here then extends towards the semiconductor double quantum dot, and there's a set of gates on top of this substrate. And one of these gates, one that lies on top of one of the quantum dots that tunes the electric potential on that dot, that orange gate here is actually connected directly to this resonator. So the vacuum fluctuations on this resonator couple asymmetrically to this double dot and essentially couple to the transition of an electron between the left and the right dot. And so if you look at the circuit diagram of this, you have a semiconductor double quantum dot, left dot, right dot. These symbols here indicate the tunnel barriers. There's a source contact, a drain contact. And the left dot is coupled to this squid array resonator. Here you see the symbols for the squid array. And then you just probe the squid array in reflection. So you take microwave radiation, you reflect it off the device, and through the circulator and an amplifier you can measure the reflected radiation. Okay, so does this work? Yeah, so here's another expression for the squid. The interesting bit also about this squid array is that now you can tune the critical current in a squid by applying a magnetic field. Yeah? So you can tune the critical current of every one of these loops by applying an external magnetic field, and that then tunes both the inductance, and through the inductance then the resonance frequency and the impedance of the circuit. And this you can then verify easily. You do a microwave reflection spectroscopy experiment. So that this here is the S11 parameter, so the scattering matrix measured of this device in reflection. At 0 applied magnetic field, you see a maximum frequency resonance at around 6 gigahertz, and then you apply magnetic field, and the resonance frequency comes down. And by analyzing this spectrum here, you can extract the resonance frequency, and you can also learn about the impedance of this device. And so this particular device has then an impedance of, say, up to 2 kilo ohms. Yeah? And so the ratio of this realized impedance to like a typical 50 ohm impedance gives you the increase in coupling strength that you have realized. And because it's only the square root of that ratio, yeah, the coupling strength increases sort of moderately. Yeah? And so you might say, was this really worth it? But this was about the factor that we needed to go from, okay, it doesn't quite work, to yes, it works with reasonable qubit coherences. And it also shows you that you will not make this factor 100, yeah, because you can't make a resonator with an impedance that is many hundreds of kilo ohms. Okay, and then you can measure the line width of this resonator, and currently the line width of these resonators are not as good as we wish for, but they're good enough for reaching the strong coupling limit, and I can comment on that later. Okay, so then you take your semiconductor double quantum dot, and really the way how you look at the physics is you can draw this energy level diagram. There's a Fermi level on the left in the source, there's a Fermi level in the drain, and then there's these two quantum dots where the energy levels are mostly determined by the charging energy of the charges on the dot. And so even though that there's maybe more than one electron on each dot, the separation between these electronic states is dominated by the charging energy, which is just the capacitive energy for adding an electron to that dot. And so you can then tune voltages up on these gates to bring two of these levels in the vicinity of each other. And if you control the distance between the two dots, you can control the tunnel coupling rate between the two. And these two states will then hybridize in sort of bonding and anti-bonding orbitals, so symmetric and anti-symmetric superpositions of having either an electron on the left or one on the right. And so this is then here the energy level diagram versus this detuning parameter little delta, which is the energy difference between sort of the charge state in the left dot, the charge state in the right dot. And the minimum transition frequency occurs at the tunnel coupling. So the minimum transition frequency or the minimum level separation that you could realize is given by the strength of the tunnel coupling between the two dots. And now you can use this detuning the local energy levels on the left and on the right. You can change the transition frequency of this double quantum dot. And if you choose parameters right, then you can make this double quantum dot energy levels intersect with or get in resonance with the resonance frequency of the microwave frequency resonator. And here you would then expect the vacuum Rabi mode splitting to be observable. So here's then a measurement of the reflection spectrum of the high impedance resonator versus the detuning between the left and the right quantum dot. And you see that the resonator then gets, as the quantum dot approaches from above, the resonator frequency gets pushed downwards. Like here in the middle, you would expect some anti-crossing and the vacuum Rabi mode splitting, and the quantum dot goes through its, the double quantum dot goes through its minimum transition frequency and then comes back up. And you can now already from the frequency shifts, you can do a master equation simulation and using the line width of both the cavity and the quantum dot to try to analyze the parameters, the cavity QED parameters of the system, and which include the coupling strength G, the energy relaxation rate of the quantum dot, the dephasing rate of the quantum dot, and the line width of the cavity. And so this is mostly from this dispersive data here. And so here you would already see, the coupling strength is larger than any of this decoherence rate, and so therefore this should go into the strong coupling limit. And you see it both from the line width of the resonator and also from the frequency shift of the resonator. But then you would like to go into resonance and see whether you can actually observe a vacuum Rabi mode splitting. And lo and behold, you see that we could observe a vacuum Rabi mode splitting for charges in this semiconductor double quantum dot. And the coupling strength 2G here was about 240 megahertz, and the line width was about 90 megahertz or so. So that just barely made it, and now you could ask, okay, why did it make it? And it's exactly this factor of 5 or so that we got from this trick with this impedance that moved this from not working to be in the strong coupling limit. And then you can sort of use that and use these cavity QED techniques, circuit QED techniques to learn more about the system. And what I should also say is that similar experiments were done simultaneously in the group of Jason Petta in Princeton.
Operationally, how do you figure out delta? You're tuning some voltages and then...
You look at there's honeycomb diagrams, and you can calibrate how the levels move around with respect to the voltages, and there's cross couplings between all the elements. And so that takes a little bit of experience to do it, but in the end you can calibrate delta. And what is also nice is that the resonator itself introduces a fixed energy scale, which you know, and then you can refer everything to this fixed energy scale that you know, and look at what voltages different states come into resonance with this resonator. I could show you some pictures. Okay, so now there is strong coupling, and so we were happy because this strong coupling then allows us to do all the other things that we like about cavity QED. Yeah? So we can think about performing qubit readout. We could maybe think about doing non-local coupling between qubits. We can do charge qubit to photon conversion, maybe do spin qubit to photon conversion, and this might be nice for doing non-local couplings in quantum information processing. And so maybe very broadly said, this makes many of the features of circuit QED accessible to research in semiconductor quantum dots, which I think is a nice feature. Okay, so what else can you do? So one of the nice things about this high impedance resonator is that the resonator is now tunable by a magnetic field. And so rather than changing the bias points of your semiconductor nanostructure, which typically has some challenges associated to it, of the sort that Dan asked about, you can now tune the resonator frequency. And so here you see a combination of 4 different measurements where the double quantum dot bias points were essentially the tunnel coupling of the quantum dot was remained the same, and we've changed the detuning and then measured anti-crossings with high impedance resonator at 4 different frequencies. And this you can then use to map out the quantum dot energy level spectrum, and you see this hyperbolic dependence that was discussed before. So you could do that for spectroscopy, and then you can also do the thing that David Schuster did as one of his first papers at Yale, to use a two-tone spectroscopy to measure how the resonance frequency of the resonator changes when you spectroscopically excite the quantum dot from the ground state to the excited state. And in this type of measurement, you can also extract the quantum dot spectrum spectroscopically, and then measure the quantum dot line width in this spectroscopic way when it's detuned from the resonator itself. And so when you see that, and when you see that you have a line width that is sort of reasonable, that tells you that you can probably do time-resolved measurements and maybe spectroscopy. So here's a spectroscopy of this double dot charge qubit for different microwave frequency drive strength that are resonant with the quantum dot. And when the drive strength is large, you power broaden the transition, and if you turn the drive strength down, you will see the intrinsic line width of the double dot. And now you can plot the square of that line width versus the driving strength, and then you see essentially you can get an estimate, maybe not a super accurate one, but you get an estimate for what the line width of the quantum dot transition is at low drive strength, which in this case was about 40 megahertz or so, yeah, which was about a factor of 10 or so smaller than all these early experiments. So we both got in this device larger coupling strength and also better coherence properties. And this was even already, we thought, oh, this is surprisingly small. Why is it so small? I think there were papers that you can read where people say, okay, you couldn't reach that small line width. And so that motivated us to also look at second generation devices. And here I should mention that there's this nice paper from Jason Petta's group that does that on silicon germanium quantum dots, and that was published in Science in the beginning of the year. And there's also a paper by the ENS group of Takis Kontos from Paris using a slightly different approach. And both of them were just made the strong coupling limit, but both with 50 ohm resonators, but slightly smaller, slightly better coherence properties, so better line widths. Okay, so we thought about what can we do better about our experiment, and we made a second generation device. And in the second generation device, we improved some basic properties. So for example, we made the resonator a bit more strongly coupled to get better signal to noise ratio. And we got a little bit better Q of the resonator. But what improved maybe most was the fact that we changed the design of our double quantum dot a little bit. And we moved away from using gold gates, which was something that people were doing for 20 years, more or less, in these structures, and tried superconducting gates. And that's also something that Jason Petta did. And with these superconducting gates, we believe it's one of the contributors to really reduce the line width in the charge qubit by another factor of 10. And why that exactly is, I think there's maybe different thoughts about that I could comment on later. So with this improved device, so now we have here's another vacuum Rabi mode splitting where 2T is coupled is tuned into resonance with the resonator, and you see this vacuum Rabi mode splitting here. And now it's much nicer. It has like the reflection signal from the cavity essentially goes down to 0 because the cavity is just critically coupled. And so you get this very nice vacuum Rabi mode splitting here. You can also repeat this spectroscopy measurements, which are shown here. So this is the resonance frequency of the cavity with the 2 anti-crossings. And then you can do this 2-tone spectroscopy technique to actually measure, to again spectroscopically measure the transition frequency of this double dot charge qubit. Yeah, now what we've seen in this particular device is that we now get charge line widths which are 3 megahertz or so, yeah, which is about 100 smaller than what we've seen in our early devices, and which is now really definitely well below of what people would have expected should be possible in these devices. So then you can do all the other cavity QED stuff. You could look at qubit photon coupling and measure the AC Stark shift. And if you measure the AC Stark shift, you can calibrate the photon number inside the resonator. So you can calibrate your external field relative to the applied external field and express that in terms of number of photons inside the cavity. And look at the AC Stark shift. And if you see the AC Stark shift, you also know that you should be able to do sort of a good measurement, or you can calibrate a measurement of the quantum dot charge states that could be time resolved. And that's then something that we tried. So here's sort of a cavity spectrum with the qubit in the ground state, which is shown in blue, and the qubit in a mixed state in orange. And you see that the cavity frequency shifts a little bit, and you could also measure the phase, and you see that the phase profile shifts a little bit. And you could do a time-resolved measurement where around this time you prepare the qubit either in the excited state or in the ground state, and you look at when you apply a microwave pulse to your cavity how the pulsed response varies independent of the state of the qubit, either in the excited or the ground state. And the difference in these two responses then allows you to perform a time-resolved measurement of the charge state in the quantum dot. So here's a set of Rabi oscillation measurements that were performed this way. So you pulse a microwave source that is resonant with the charge transition in the double quantum dot, and then you send a second pulse applied to the resonator, and based on the phase and amplitude of that pulse, you extract the qubit occupation, which is on this axis here. And we decided to do Gaussian pulses here and choose a sigma of the Gaussian pulse, which is shown here, and change the amplitude of that Gaussian pulse. So we do Rabi oscillations not by changing the length of the pulse, but by changing the amplitude of the Gaussian pulse. And then you can check, okay, how the Rabi angle depends on the width of that Gaussian pulse, and verify that it's linear as it should be. Obviously, you can then, once you've done Rabi oscillations, you can define pi pulses and pi half pulses. So here's a pi pulse, so you can apply a pi pulse and then measure the energy relaxation time of a charge in this quantum dot in just a typical T1 measurement, and just the standard circuit QED style measurement, and extract relaxation times. And what is nice now is now you can start to do experiments in which you extract properties of this semiconductor quantum dots quite accurately from using circuit QED style measurements of the coherence properties. Yeah, now you could start to ask, okay, so why is the T1 what it is? How does it depend on all the other parameters? And you can use a technique that we sort of rely on, and that we know how reliable it is, and that is from which we can extract coherence properties. Okay, so maybe one thing that was nice in this experiment that we did is that was actually the first time that rather than doing the standard thing that one would usually do, rather than using a CW microwave source, a mixer, and an arbitrary waveform generator to create these microwave pulses, we decided to go for a direct synthesis signal generator, which is not cheap, but which can do 25 gigasamples. And what is nice about that is that you can now define not only the envelope of the microwave pulse, but you can define the amplitude at every point in time. So you can do rather sophisticated pulse shaping directly on the individual on the individual amplitudes and phases of the microwave field that you apply to your circuit. And that was actually quite useful for us to do for these relatively short pulses. Yeah? So you see that a pulse with 2 nanosecond sigma or so, but still we managed to pulse shape it in a Gaussian way, and you can play some tricks to avoid leakage into other states. For example, what we try to do is with this short pulse, we want to avoid that some of the pulse leaks into the resonator, and we could shape the pulse in a way that the spectrum at the resonator frequency was 0, so that these drive photons wouldn't show up as a measurement signal in the readout resonator. Okay, and then you can start to analyze, okay, these coherence properties, and since I'm a bit out of time, I might not discuss that in more detail. Maybe you can ask me about it if you're interested. But rather, I mentioned to you like one more experiment that is currently still cold. So this is now a combination of a transmon qubit, a double quantum dot, and a high impedance resonator. So the circuit diagram is shown here. So here's the squid array resonator. There's a double quantum dot on that device. There's a transmon in this device. The transmon is coupled both to a 50 ohm resonator and to a high impedance resonator. And there's a drive line that you can drive both the quantum dot with and the squid array resonator, and and you can drive the transmon through its readout resonator, and the chip is shown here. And essentially in this region here, there's a transmon integrated into this device. And so here's the squid array that now comes from the top. The quantum dot sits here. And like one of the islands of the transmon is there. The squid is there. Here's like a flux bias line for the transmon. And the blue is the readout resonator for this transmon that you see. And now you could ask yourself, okay, is it possible to really map quantum information from a transmon to this double quantum dot and back? And you could wonder, okay, how could that be useful in the future, for example, if you want to address spin degrees of freedom, or if you want to try to look at some hybrid approach in combining semiconductor qubits with superconductor qubits. And so this also works. So we can look at both the transmon resonance with a high impedance resonator, the double dot resonance with a high impedance resonator. We can use this high impedance resonator as a coupling bus between the two. And so far, we've seen the spectroscopic signatures of this exchange coupling between the transmon and the double quantum dot qubit. And we hope that we are able to do some time-resolved measurements on these devices also in the future. So I'll just wrap up here and say, okay, like in the beginning of this year, we had this publication on this reaching the strong coupling limit of cavity QED in semiconductor quantum dots for the first time in our lab, but also in Jason Petter's lab. And this has really now enabled to do cavity QED with gate-defined semiconductor quantum dots. And maybe what I hope that would do is that people from that area will then also go to cavity QED conferences in the future. And you see sort of like if you have everything in your drawer for deploying all these techniques, you can really like in half a year you can do a good fraction of the experiments that took like 3 or 4 years in superconducting circuits to do. You can now just deploy those for these semiconductor quantum dots. So we've done time-resolved measurements, and we've got this interface between superconducting qubits and semiconducting qubits. And maybe one of the things that we look at to do in the not-too-distant future is to look at non-local coupling between charge states and possibly spin states mediated by different types of resonators. So I think it's quite promising, and so the team that has mostly worked on this is Pascale Scalino, David von Workom, and Anna Stocklauser as a graduate student. Yeah, and with that, I'd like to thank you for your attention and thank our lab for putting all the effort into making this experiments get off the ground. Thank you.
We have time for a few questions.
I have some questions on the double quantum dot side. So you're occupying it with a single electron?
No, yeah, not necessarily. Yeah, so one thing that we looked at when we did studies of the coherence properties initially, one of the questions that we had was, does it matter how many charges are in each quantum dot? Yeah? And in the early experiments, the decoherence was not dominated by anything having to do with electron-electron interaction on the dot. And so the coherence properties were essentially independent or largely independent of what the actual number of charges on this double dot was. So whether you go with 20 to 20 plus 1 or so, whether you go from 0 to 1 in the individual dots didn't make a difference at the time. And so now we can look more carefully back to that and look at the properties of coherences versus number of charges on the dots. But all the experiments that I've shown today have occupations on the dots which are on the order of several tens of electrons.
So you've done this really large improvement for this transition line width. And people, I think in the community, have started using these single triplet qubits to kind of be more robust against sources of noise. So do you predict significant improvement for single triplet qubits?
Yeah, I do think so. Even if you intend to use spin degrees of freedom in this quantum dots for defining your qubit, I think this will be good in any case. Yeah, because in many of these experiments you do some spin to charge conversion at some point. So having better charge line width would be better. And I think one of the things that is different in these devices is that we actually did go for small charging energies. Yeah? So the charging energies in these devices are much smaller than charging energies in typical devices. And that's a little bit like what happened in transmons. So what is the difference between a Cooper pair box and a transmon? It's the fact that the device has much more capacitance. And this larger capacitance actually reduces the effect of external voltage noise wherever it may come from. Yeah? And so if you say you have given voltage noise on your leads, on your gates, and the capacitance of your device is larger, so the given voltage noise will lead to less dephasing on the device, and that's one of the things that mattered. And maybe the fact whether you have a normal metal gate or a superconducting gate might make some difference in terms of the noise, maybe the residual noise that you might get from these leads, but that we need to look at a little bit more. So both Jason Pettas and our devices have these aluminum gates, which seem to be an important aspect.
So from the look of the people in this picture, I take it you've made an important discovery. So what do you...
It's this guy's lab book, yeah?
Yeah, we discovered it. What physics will we discover from these techniques?
Okay, so in semiconductor quantum dots, so one thing that I was actually motivated by was, I think that there were, like, people made statements about what was limiting the coherence in these devices, and I think they weren't very justified. It felt to me a little bit like, okay, there was always, like in the early days of ion traps, there was lots of discussion about patch potentials on electrodes. Yeah, and my feeling as a solid state physics person, I said, okay, these patch potential, that's nothing intrinsic with it's nothing that has to do with the metal that you're using in your device. Yeah, and nevertheless, everybody sees this problem. Yeah, and then Dave Wineland goes ahead and puts an ion gun into his system and gets rid of these patch potential, and now it's much better. And sort of it's sort of a little bit similar here. There's sort of, you have superstitions on what should limit coherence in these devices, but it wasn't really thoroughly checked at the level that you would really want to, whether this is what the physical mechanisms really are. And I think if you have now this more sensitive techniques, you can actually look in much more detail at these physical mechanisms, yeah, and look, for example, at branching ratios. And so does the electron now relax by making a phonon into the substrate, or is it a photon into the environment? And if yes, where does the photon in the environment go to? Sort of, I think this is really something that would motivate us, and I do think that since we have this really very nicely packed superconducting circuit toolbox, I think it can do a lot for these semiconductor works.
So you showed us the sort of population decay time of like 20 nanoseconds or something.
Yeah.
If I was to do Ramsey spectroscopy for this and measure a T2 time, how would that compare to that sort of population decay?
So the two slides that I skipped had measurements of T1 and T2 versus system parameters. Yeah, and you can be in a limit where it's T1 limited, and then T2 is close to 2T1, but it could also be different depending on where you are biased. So you see still, like at finite deltas, you still see voltage noise limiting the T2, and that's something that we would like to look at. Yeah, like do we understand T1 and T2, and how does it depend on system properties? So, for example, one thing that is bad about gallium arsenide is that it's piezoelectric, and quite strongly so, and that will couple charge phonons more strongly in these devices. And how strongly, I would hope we could actually do a sort of a good investigation on with these types of techniques.
Okay, the spirit of Dan's question about a physics perspective. So in double quantum dot community, the typical experiment is a transport experiment. So
yes.
Does it work in this microwave regime?
Yes. Yes. So one of the experiments that we did, and we had Anna Stockklauser had a PRL paper on that. So we can bias. So the best coherences we obviously get when the tunnel coupling to the source and the drain is 0. Yeah? But you can open the tunnel couplings to the source and the drain and look at transport. And that will affect coherence. But you can, for example, look at correlations between charge transport and radiation creation. And that's, for example, something that I find very interesting. And we've done some first experiments before, but in the paper that we've published, per electron, because we were in the weak coupling limit in that paper, per electron, the probability of actually creating a photon in a resonator, even if it was nominally resonant, was only 10 to the minus 4 or so. Yeah? And it was coherence limited, and we understood that. And I think what this is also nice for is if you look at correlations between charge transport and sort of radiation emission, maybe both in the photonic branch but also in the phonon branch. I think that there's lots of things that could be interesting, I think, in terms of doing transport mesoscopic physics on a wide range of semiconductor nanostructures using this approach.
Okay, so let's thank Andreas again.